Hi everyone, my name is Idris Kempf and I am a DPhil student from the Department of Engineering Science of the University of Oxford. In this video, I'll present my paper entitled Fast Gradient Method for Model Predictive Control with Input Rate and Amplitude Constraints. This is Diamond Light Source, the UK's national synchrotron facility. You'll notice the tiny cars in the foreground. This oval-shaped building has a circumference of more than half a kilometer. As part of my DPhil project, I'm developing and testing a control system for Diamond Light Source. The control system controls more than 250 inputs in a feedback loop running at 100 kHz and regulates the position of the electrons that are traveling around the ring at the speed of light down to nanometers. Because of strict actuator constraints, I'm implementing model predictive control. In the end of the talk, we'll come back to the particle accelerator and compare their performance. Let's get started with the problem statement. This is our standard linear MPC problem. The first line describes the objective function that we try to minimize. The first term, xk weighted by q, represents the displacement of the electron. The second term, the input energy, and the last term, the terminal cost, where the matrix P is obtained from the corresponding infinite horizon problem. The problem is subject to constraints, and the system dynamics are governed by the controllable pair A and B. At each time, the MPC problem is initialized with an initial condition x of t. Once a solution to this problem is found, the input is applied to the physical system, and this whole procedure is repeated at the next time step. For our particle accelerator problem, we are allowed to omit the state constraints. This will greatly simplify our problem and allow us to substitute the system dynamics. Doing so leads to the standard constraint quadratic optimization problem, where we assume that the matrix J is positive definite. The input constraint set is represented by calligraphic U and, as we will see on the following slides, is a convex set. We'll now examine the building blocks of the input constraint set before showing that it can be represented as the intersection of several smaller sets. The inputs in our system have a limited amplitude. The amplitude constraints apply independently to each part of the input sequence and element-wise to each component of the vectors. Here we choose to group the constraints at time k and k-1. An orthogonal projection onto this set is shown here. It is mathematically given by the saturation function, which limits its argument to plus minus a. In continuous time, the slew rate constraints limit the time derivative of the input, and in discrete time, they limit the difference between two subsequent inputs. In contrast to the amplitude constraints, the slew rate constraints couple the input sequence u0 to uh-1. A projection onto this set, as shown here, also makes use of the saturation function. The rate constraints also apply element-wise to each component of the vector. And from now on, we'll assume that the inputs uk are scalars. We will remove this assumption at the end of our talk. For further developments, we now choose to intersect these two sets, yielding the building blocks of our constraint set, which we shall call calligraphic uk. The whole input constraint set can be obtained from intersecting the smaller sets. The first input u0 is affected by the input at time t-1, and the set calligraphic u1 therefore looks different. Also note that these sets contain overlapping constraints. Input u1, for example, is affected by constraint set calligraphic u1 as well as constraint set calligraphic u2. Before examining the orthogonal projection onto this set, let me present the fast gradient method and the alternating direction method of multipliers. First order methods are algorithms that use the objective function itself and its first derivative, but no higher order derivatives. In contrast to higher order methods, they usually yield lower accuracy solutions but are faster. In the context of feedback control, however, a low accuracy solution is often sufficient. The first algorithm we will outline here is the fast gradient method. In our paper, we use the constant step scheme suitable for strongly convex objective functions, a variant that comes with as little overhead as possible. One iteration of this algorithm is shown at the top of this slide. where PU denotes the orthogonal projection onto set calligraphic U, and nabla F the gradient of the objective function. This equation maps to the following arithmetic. The first step consists of vector additions. The second step is defined by the gradient descent step. Computing the gradient of our objective function consists of multiplying the objective function matrix J with a vector. The last step is the orthogonal projection onto the input constraint set. No explicit solution to this orthogonal projection is known, and we will need to apply an iterative algorithm. The second algorithm we will look at is the alternating direction method of multipliers, abbreviated as ADMM. For applying the algorithm, we need to reformulate our problem. The first step is to rewrite the constraint set as polyhedron. The second step is to introduce auxiliary variables v that account for the constraints. The last step is to assign the dual variables gamma to the equality constraints between u and v. This function is the augmented Lagrangian of our problem and is now repeatedly minimized with respect to u and v and maximized with respect to gamma. This is shown on this slide. The algorithm maps to following arithmetic. The minimization with respect to u is usually found by solving a system of linear equations. Note that after introducing the auxiliary variables, this step represents an unconstrained minimization. The constraint minimization now happens in this second step. The solution to this problem, however, is straightforward and given by the element-wise application of the saturation function. The third and final step of ADMM consists of updating the dual variables and essentially adding a few vectors. For the fast gradient method, as well as for the ADMM, we can choose to run their 3 steps for a fixed number of iterations or to implement a termination criterion. Note that it is possible to compute the required number of iterations in order to achieve a certain suboptimality level for a given MPC problem. Now let me briefly compare these 2 first-order methods. Due to the introduction of auxiliary and dual variables, the number of decision variables for our particular constraint set is 4 times larger for the ADMM algorithm. Implemented on an embedded system, where memory accesses usually represent a bottleneck and where only limited resources are available, this might pose a problem. The main workload for ADMM is finding a solution to the linear system, and it's a step which is usually hard to parallelize. For the fast gradient method, we expect the main workload to be the matrix vector multiplication or the iterative projection algorithm. For this particular constraint set, the main drawback of the fast gradient method is that the projection is a priori unknown, and for the ADMM it is given for the saturation function. The convergence properties are comparable in practice. While it is proven that the fast gradient method has the best possible asymptotic convergence properties for our class of problems, it is also known that the method is affected by ill-conditioned problems. In addition, we do not exactly know how the iterative projection algorithm will affect the convergence properties of the fast gradient method. This last statement brings us to the second last section of this talk. The orthogonal projection onto the input slew rate and amplitude constraint set that is required for the application of the fast gradient method. The orthogonal projection itself defines a constrained quadratic program. Recall that set calligraphic U represents the input rate and amplitude constraint set, and that set's calligraphic UK represent 2 grouped amplitude constraints and 1 rate constraints that affect elements UK and UK-1 of the vector. The difficulty of finding a solution to this problem depends on the horizon length h. We can identify 2 special cases. For h equal 1, the set U represents a rectangular box. In this case, the solution to this problem is given by the saturation function. For h equal to 2, we can make use of a geometric approach to solve the projection. This will be presented on the following slide. For larger horizons, finding an analytical solution becomes quickly intractable. One can see the above problem also for horizon equal to 2 as a multi-parametric program with parameter u superscript 0. The solution to this program will be a piecewise linear affine function that is defined on different sets. The number of sets, however, will grow exponentially with horizon length h. We therefore decided to make use of an iterative approach where one projects onto larger sets by applying known projections onto its building blocks. Our building blocks are defined by this picture. I introduced the regions AI, BI, and CI. This picture basically corresponds to a visualization of the solution to the multiparametric program. If the starting point lies in BI, then the projection is given by the saturation function with limits plus minus a. If the starting point lies in AI, then we need to project onto the upper or lower diagonals. If the starting point lies in one of the corner regions CI, then we need to map to the corresponding corner points. The particular geometry of this set yields to an additional simplification. We can group regions AI and CI and project onto this rotated box. Great. Now that we know how to project onto each of the sets UK, we can apply Dijkstra's algorithm. If a convex set can be represented as the intersection of a number of sets for which the projections are known, Dijkstra's method projects onto the original set by iteratively projecting onto its building blocks. For our problem, note that the projection onto each of the sets UK only affects two subsequent components of the vectors, UK and UK-1. We can simplify the algorithms by grouping sets UK by even and odd indices, obtaining sets U even and U odd, for which we do know the orthogonal projections. For this partitioning, Dijkstra's method works as follows. We first project onto U even and save the difference between the obtained point and the argument of the projection into delta even. We take the obtained point, subtract the last difference from the projection onto U odd, and project it onto U odd. As we are progressing, our iterate will approach the orthogonal projection onto the intersection of U odd and U even, our input rate and amplitude constraint set. This is a brief visualization of Dijkstra's method with two arbitrary sets, S1 and S2. The starting point is x naught and the orthogonal projection is x star. You will see that as the algorithm continues, we'll approach the orthogonal projection S star. We will compare ADMM and the fast gradient method using Diamond's electron beam stabilization problem. What we see on this picture forms the heart of the particle accelerator, the storage ring, a large oval-shaped ring around which the electrons travel at the speed of light. While they do so, they emit the so-called synchrotron light, which is used in the experimental stations, most often referred to as beamlines. These beamlines are home to various kinds of microscopes. For example, Diamond's unique electron cryon microscope, which was used to examine COVID-19 samples. Among the numerous control systems which this complex machine involves, we are interested in controlling the magnets that guide these electrons. More specifically, we are interested in the feedback system involving the corrector magnets. This loop runs at a frequency of 100 kHz and uses 250 measurements to control 250 inputs. The system regulates the displacement of the electrons from their ideal orbit paths and limits their deviation to 600 nanometers. With that said, we arrive at the comparison of the performance. For this proof of concept, I have implemented the fast gradient method as well as the projection algorithm in C. I made the code publicly available on GitHub. I'm comparing my implementation against a well-established solver that uses ADMM, the operator splitting quadratic program solver developed by the University of Oxford. I have disabled adaptive step sizes and solution polishing, and I implemented a closed-loop simulation of the MPC problem and averaged the timings over 1,000 problem instances. For the purpose of comparing the two methods, I have also implemented a termination criterion and made sure that both algorithms obtain a solution with the same accuracy. For Dijkstra's method, I'm using a fixed iteration number. The required time per iteration can be seen on the left-hand side of this slide. It isn't surprising that for horizon 1 and 2, the fast gradient method outperforms ADMM because we can accurately project onto the constraint sets. For larger horizons, however, the overhead introduced by Dijkstra's method is surprisingly small. This picture looks slightly different for the total execution time per MPC problem. While we retain the major speed advantages for smaller horizons, the fast gradient method combined with Dijkstra's method does need a higher number of iterations in order to reach the same accuracy. Also note that larger horizons negatively affect the condition number of the objective function matrix, which in turn affects the convergence properties of the fast gradient method. With these results, we have closed the speed gap significantly, and other work we are doing will, in combination, enable us to reach the 100 kHz. With that said, we arrived at the end of my talk. In this presentation, we saw an efficient method to project onto the input rate and amplitude constraint set. We saw how the combination of Dijkstra's method and the fast gradient method outperform ADMM for this particular set, but we also saw that the speed advantage is smaller for larger horizons. We are currently focusing on extending convergence proofs for Dijkstra's method and experimenting with acceleration methods. We are also interested in deriving suboptimality certificates for the combination of the fast gradient method and Dijkstra's method. My name is Idris Kempf, and I thank you very much for watching the video.